introduction and for inviting me to talk. I'm really excited to be here. All right, so concrete. We are going to discuss concrete. All right, so one of the reasons that we're really interested in a lot of our infrastructure materials is actually tied to consumption patterns. So the statistics I'm showing you here are actually our most consumed materials worldwide, and you'll see this massive gap between our concrete and all of our other materials. In fact, there are many more materials that I don't even have plotted on here, in large part because you will stop seeing them past aluminum. So aluminum is technically plotted on this chart, you just can't see it. Now, you also see there's a little squiggly mark next to the amount of concrete consumption that we have, and that's because we actually don't have remarkable statistics for our concrete consumption. In large part, it's because this isn't a widely traded material. It's something that consumes localized resources, and as a result, we don't necessarily monitor those resources, and we right now actually have something that's referred to as the sand wars, basically social and political unrest associated with the consumption of resources to produce concrete. Now, concrete, relative to other materials, as you can see from the chart, pretty high, but relative to water consumption, still relatively low. So this is our most consumed human-made resource, but we are still consuming a lot of water. Now, the reason we need so much of this particular material is because we use it for everything. So I recommend that as you walk out of this room and have, breaks, chats, etc., look at the world around you and you'll see how much of it we managed to cover with just one material. We're using this for our roadways, our buildings, our foundations, our sewer systems, which hopefully you can't see, as well as our bridges and other applications. So, as we have a growing population, we expect to see more of this material consumption. So basically, more people, need for more roadways, need for more buildings, need for more bridges, etc. This is problematic in large part because we keep making more of ourselves. So hopefully you're aware in 2022, we actually passed 8 billion people on the planet. If you kind of look back in 22-year increments, going back a little ways, you'll see it's a nearly linear increase of how many additional people we're adding each year. Obviously ups and downs in small blips, but in general, that's kind of the trend we're following. If we then think about this with the perspective of, okay, more people, we need to actually make sure that they have access to clean water through pipes, get rid of the refuse away from the sewer systems, make sure they're able to get to educational facilities, hospitals, etc., great, more concrete for all of these applications. We also need to think about this from the perspective of the purchasing power. At the same time that we have had a growing population worldwide, we've also had growing affluence worldwide. Again, individual dips, individual regions not necessarily going in the same direction as others, but in general, we've been able to afford more stuff as time goes on. This causes a huge environmental challenge. So basically, it's a little bit simplified, but you can kind of think of our environmental impact as a function of our population, our affluence, and our technology. The more of us and the more we can afford, the more environmental impact we are going to have as a planet of people. So the only way that we can potentially reduce those impacts, assuming that we kind of keep going on our current trajectory of more people and more affluence, is through technology. And now we have to think back to that one material that I called out. Yes, concrete. And yes, the Romans were making it too, but the technology has slightly changed. If you want to nerd out about Roman concrete, I am happy to, but we won't do it right now. Concrete is composed of a few really commonly available materials. Basically, water, cement, and crushed rocks, otherwise known as aggregates. We end up using the water and the cement as a binder to hold together aggregates, but by and large, concrete is made out of the crushed rocks. It's the largest volume constituent that we're putting into our concrete. Now, crushed rocks, sand, aggregates, we have those widely available in general. There's a few places where we actually have scarcities, where we don't have enough of those sand and other components to support our concrete production. But usually we have those in regions that are able to do quarrying locally. This is why we're not monitoring it particularly well, which is what's leading to the sand wars. Cement is a hydraulic binder, and it interacts with the water, holds together the aggregates, forms a synthetic rock. We put that synthetic rock everywhere. Cement, in case you haven't maybe been as following as I am, since I am very closely following leads to pretty substantial global greenhouse gas emissions. This is actually a function of the level of consumption. The material itself is really not that bad for the planet, especially when you compare it to some of the other materials I had on that bar chart. It's actually a really low greenhouse gas emissions material, but then when you produce 4 billion tons of anything, it's going to have a high impact. When we're producing cement, the way we manufacture it is we take limestones and clays. We use the limestone for the calcium, the clays for the amorphous silica that we need. We decarbonate our limestone. We basically take calcium carbonate and then turn it into calcium oxide, which means we already shoot off a fair bit of carbon dioxide that was otherwise in a nice stable mineral. We then continue to heat the material to form calcium silicates. Those are the hydraulic compound that can then interact with water, pull together the aggregates. Fantastic. That second stage of heating is usually in the 1450 to 1500 degrees Celsius, and we're big fans of using fossil fuel for that particular stage of heating. In fact, I was very upset to hear that in California, our current only use of coal is in our cement plants. So we're actually still highly reliant on fossil fuels for this particular application. Now, cement is not alone where you have these kind of chemical reaction-derived emissions as well as energy-derived emissions. In fact, a lot of the materials that we consume a lot of have something similar to this. So for example, steel, we need a heck of a lot of steel. The way that we're currently producing steel from virgin resources, so not our recycled steel, basically to get our iron oxide to turn into iron that we can then combine with a wee bit of carbon, we do a redox reaction. Our current way of doing that redox reaction is we use coal to form carbon monoxide, which we then interact with the iron oxides to form iron. So there's a chemical reaction-derived emission, and then of course we're doing that at a relatively high temperature, energy-derived emissions on top of it. So we know, okay, if we need a heck of a lot of these materials, we've got energy and chemical-derived emissions, we have a greenhouse gas emissions problem. In fact, the production of cement and concrete is currently leading to an estimated 8 to 9% of our energy and process-derived greenhouse gas emissions. Now, this is not including our agricultural-derived emissions or any of the emissions from our regular forest fires, but of the emissions that we have direct control over, we are seeing a heck of a lot of it coming from the production of one material that we're using around the world. Now, anything that's leading to that high of emissions in one category because of consumption is going to lead to other substantial impacts. And this is not paid as much attention to. So right now, for example, California was one of the first locations in the world to pass a bill to decarbonize cement production. So we have what's referred to as SB 596 and Bill 596 that basically says the use of cement in this state has to hit net zero by 2045. So this includes the cement that we're importing. But it doesn't say anything about our energy demand to produce these materials, the water consumption levels, our air pollutants, and as you can imagine, those don't all have the same scale of impact. We're all dealing with climate change in very different ways, but climate change is a global burden. However, air pollutant emissions are local. Those are going to harm the populations that are actually inhaling them. And this starts to cause an additional political divide of, if I'm trying to meet a decarbonization goal, how do I make sure I'm also not harming the neighboring community? How do I make sure I have a co-benefit when I start to implement one of these strategies? And that becomes very tricky when you start to realize that while cement is the primary driver for producing greenhouse gas emissions from concrete production, because it was the only one that actually had to get processed, the rest of it's just crushed rocks and water, we end up seeing that that's not going to be the same case for some of our other impacts. I'm using water as an example here just because my parents are farmers and we have a significant reaction to all the droughts and over excess of water that we have in the state. There's farmers in California. So we will have these fluctuations of, oops, we have not enough water for our crops. Oops, now our fields are flooded. So paying attention to this local resource of water ends up being kind of an interesting juxtaposition. So you'll see the greenhouse gas emissions all tied to cement production. The water consumption associated with this product, it's not even tied to the fact that we use water in concrete. That's the little orange bar. That's the constituent that's water. The rest of that is actually water that we're using for processes and energy to produce each of these constituents. So if you think about this in terms of a breakdown, we'll see that, yeah, about 10 to 15% of the water that's consumed for concrete is because we put water in concrete. But We have a huge amount that's tied to the energy to actually produce these materials, a wee bit that's actually tied to the energy resources for transportation, and then a lot that is tied to the processing. So this includes things like dust suppression, as well as factors like actually making sure that we have a washout for our concrete trucks. So actually making sure that we don't have concrete that gets stuck inside of those spinning trucks. So as we start to look at this, it could start to appear as an enormous challenge, and I do apologize for the yellow glowing. It's not symbolic of anything except for Microsoft got angry at me. But basically what we end up seeing is, okay, we're consuming a lot of a particular class of materials. This huge level of consumption is leading to various different impacts. Some of them are localized, some of them are global. But it also presents a huge opportunity. And this is actually one of the areas that our research group, along with a bunch of different collaborators, are working on, which is, if we're consuming this much of one thing, can it act as a ground level reservoir for carbon dioxide? So we're not reliant on below ground reservoirs. So we're looking into strategies for carbon dioxide removal that could then get stored in our built environment if this is our largest consumption of materials. Now, in this particular area, we're not focusing exclusively on concrete. We're looking at emissions from various sources. Did you capture it directly at an industrial flue? Did you capture it from the ambient atmospheric CO2? Are you able to do something like mineralize this material? Mineralization facilitates a much more long-term storage facility. Or can we potentially leverage biogenic resources? Biogenic resources tend to not be quite as long-lived because many of them have natural microorganisms available that can help break them down, whereas our mineralized structures can last a little longer. And we're looking at different ways of starting to integrate these into the built environment, including things like potentially solidifying our cement through carbonation as opposed to hydration, through the formation of synthetic aggregates, through the utilization of biogenic resources in concrete, as well as quite simply using biogenic resources as the components themselves in the built environment. And one of the reasons this ends up being so interesting is that if you start to pair this with our idea of how much energy and food we need as a society, we can actually see where some of our balances start to play out. If we look at our consumption from 1900 to 2015, the vast majority of our consumption was actually for building materials, and we were building up many societies during that particular period of time. It, relative to our demand for food, energy, and feed for animals, livestock, etc., is actually almost on par. We almost consumed about as much building materials as we consumed resources for energy and for food. But of course, we need food, and we're big fans of energy, as you heard from our last two talks. So let's think about this from our energy generation and our food production standpoint. If we're going to keep producing food, then we're going to have a certain amount of residues that aren't necessarily used directly in that food product. Can those support our production of energy resources? We're actually working with several of the biological and agricultural engineers on campus to explore how much can we remove from a field, still facilitating no degradation of soil health and making sure that we're able to produce a fair bit of energy. Those will have a certain amount of byproduct materials, which can then be potentially integrated into the built environment. We're trying to pair off a bunch of different optimization patterns in order to inform that. So just a couple of kind of food for thought ideas as we're stepping away. We are actually able to synthesize a concrete-like material. It's not technically our conventional Portland cement concrete, without use of any Portland cement and utilizing biogenic resources to help supplement some of our aggregates. As you can imagine, they perform a little bit differently, but we're actually able to synthesize a material that is very, very similar to what we're seeing in our conventional built environment, but that's using waste products from agricultural resources. We also are looking into the generation of various different bioplastics using, again, a wide range of bioresources that are available. These include things like waste from fields as well as food waste that we as a society generate. Each of these can form different types of plastics that could then potentially offset our concurrent plastics consumption. We're also looking, of course, into wood, since that's our fan favorite of storing biogenic materials in the built environment, but I only had a limited period of time, so any other interest in discussing our carbon dioxide removals and storing in the built environment, I'm happy to discuss at a later stage. But I do need to thank, well, all of the groups that have actually supported this research. Most interestingly, at least to me, this includes the Department of Defense. They are concerned about this as well. But of course, there were many others besides just the Department of Defense. And even more importantly, I need to thank my graduate students and postdocs because, of course, this is all their work that I've just shown you. And of course, we also have many collaborators on campus as well as at the national labs and other institutions. So much so that we actually just started a research center, which is what's labeled up at the top, where we now have industrial affiliates who are also trying to partner into trying to understand how do we start to offset some of these impacts that we are creating. That is it in terms of slides, so I'm happy to take any questions.
Any thoughts as to the hope of recycling destroyed concrete, given that I'm thinking of the various wars around, or should we simply accept it as carbon storage?
I have so many thoughts on that. Okay, so, all right. First of all, it actually looks as though we can recycle certain components of our concrete through pairing them with other industrial systems. Right now, our biggest way of recycling concrete is crushing it and using it as road base, which is considered actually downcycling. It doesn't really perform the same way, but we can break apart our aggregates and our hydrated cement and actually send them through electric arc furnaces, which is what we use for steel recycling, and get very, very similar compounds out. We haven't scaled this yet as a society, but yes, there is absolutely potential to recycle this material.
So there's a big industry related to all this. When you go and talk to people who make lots of money from cement, what do they think about all this? What's their attitude?
They're on board. So actually, some of the industrial affiliates are cement producers that are both based in California and worldwide, so Heidelberg, Cemex, et cetera. Very interested in decarbonizing, I think in part because they're starting to see some of these bills come out that are saying you have to hit net zero and they would like to stay in business. So they would like to understand what else can they do with their material or with their manufacturing supplies to stay there. Yeah.
Any last questions? There's one over there. Great, thank you.
First, thanks for a fascinating talk about concrete. I didn't know I was going to get that today, so thank you. I was wondering, I'm pretty sure you said that in California that is it all of the coal that's being used is in this process for heating? Is it, what
Nearly all. I'm sure someone will find like one other tiny application that is getting used, but the vast majority of the coal that we still use in the state is going to cement production. Yeah.
So I was wondering, are there other mechanisms people are thinking about for trying to heat up the kilns to the temperatures that they need, like solar thermal or some other sort of form of energy people are thinking about?
Yeah, a lot of folks are looking into, well, actually in California, interestingly enough, we use shells from certain biomass because the density is enough so that you can get the right energy out of them. But folks are also looking into recapturing methane from landfills, as well as California has a bunch of startup companies that are trying to get batteries that can hit the right temperatures out at these industrial facilities. So there's a bunch of different strategies that people are looking at to reduce that dependence on fossil fuels.